Okay, so now we are going to the next part. We will actually talk about the quantum description of materials. I hope my screen is visible, right? Okay, it's visible, right?
Yes, sir.
Okay, so when I'm talking about quantum description, that means we are of course going to talk about quantum mechanical features. So let us see what is it. So when we are talking about a material, or let's say any kind of material, then it is consisting of several atoms. So that is the building block. Okay. Now these atoms are made up of nucleus and electrons, and as we know that they interact with each other. How do they interact? They do it via something called as Coulomb interaction. Okay. Now there are more than one electron, so we can take them as something called as a many electron system. Okay. So if there are more than one electron, so it becomes a quantum mechanical many body problem, and we have to solve the Schrodinger equation for interacting electrons and nuclei in order to find out what sort of energy spectrum or wave function that is being generated as a result of this interaction. I hope this part is clear. When we are talking about electrons, then there are two types of electrons in a material, or let's say in an atom. So one is called as valence electron and other is core electron. So let's say if we are taking the example of sodium, then we know sodium has 3s electrons. So this is the electron which is present in the valence shell. That means in the last orbit. So this is called as valence electron. And this particular electron is responsible for most of the interactions, activities, reactions, things like that. Okay. So whenever let's say there's some interaction, this electron will probably jump. If there is a spectroscopic transition, that electron will be the first one to take part into it. And also if sodium reacts with chlorine, then also this electron will form the bond first. Okay, so this electron has a big role, and the reason is that since it is in the valence shell, so it does not have to or let's say one does not have to cost a lot of energy to basically knock out this electron, or let's say make this electron interactive. Okay, now the rest of the electrons are called as core electrons. So these are the electrons which are actually located deep inside the cells. Okay, so we have valence cell and then we have inner cells like 1s, 2s, 2p, and all these things. So these inner cells, they are basically those electrons which are located there. They are called as basically core electrons. Okay. Now, as I just said, that valence electron they determine the property of a solid. Now, there are entities. So, there is core electrons which actually can combine with the nucleus. So, we call that entity as ion. Okay, and then we have the valence electron. So, basically, an atom can be considered of a sum of an ion and valence electron. Now, in any condensed matter system, we get basically, or we can consider it as a many body system of interacting electrons and ions, and we have to find a solution of that. So, is this part clear to everyone? Any question, confusion? Anyone? No? Okay. So now we have to solve this many body problem. So there are, so as I said, that we cannot directly solve this thing. We have to take some approximation, and there are several approximation methods. Which are they? The first one is called as Born-Oppenheimer approximation. Second one is called as Hartree approximation. third one is called as Hartree Fock approximation, and fourth and the last one is called as density functional theory. Okay, so these are the four methods in which you can actually solve this problem. Now let us look at what is Born-Oppenheimer approximation. So Born means Max Born, and Oppenheimer is again the scientist Oppenheimer. Okay, so I am hoping that Born-Oppenheimer approximation somehow you guys are familiar with. Okay, still we'll discuss it. So what this approximation says is that you have to decouple the electronic and ionic motions. Okay, so as I said that we are treating an atom as a sum of an ion and an electron. Okay, so very simply, let's say if I am talking about a sodium atom, so I am taking it as a sum of sodium plus and electron. Is this part clear? So this is my ion and this is my valence electron. Okay. So here what we are doing is that we are decoupling the electronic and ionic motions. Okay. So we are saying that these are separate entities. So the second point is also saying the same thing. Now, usually the number of electrons and ions, they are quite large. So typically of the order of 10 to the power 24. So finding an exact solution will be difficult, but we can get an approximate solution by separating the electronic and ionic wave functions. Okay. Now ions are heavier than electrons. Can anyone tell me why ions are heavier? Yes.
So ions are comprised of electron and the nucleus. So nucleus is heavier and rest of electrons also,
Very good.
except valence.
Okay. Yes, since ions have nucleus in it, so that is why it is quite heavier, and typically it is 10 to the power 3 to 10 to the power 5 times heavier than the electron. As a result, they will also move much slowly. Okay, so when you are talking about the ionic motion, the motion will be much slower compared to the motion of the electrons, and the time scale of this motion is also different for the electronic motion and the ionic motion. Okay, so is this part clear?
Yes, sir.
Okay, so now I am going to a famous example which I explained to you at the beginning of this course. Okay, so in order to understand the difference of this time scale, let's take this particular example of elephant and bees. Okay, so I'm quite actually surprised to see that I have drawn a nice elephant. Huh? Do you think this is nice or this is not nice?
It's really good.
You think so, right? Ah, okay. Now, this particular leg is a little bit weaker compared to this front one. Hmm. That is not realistic. Okay. So anyway, okay, it's an elephant, and I'm not M.F. Hussain, so we have to go with it. Okay, so let's say this is an elephant, and these are the bees. So here, the ion is something which is equivalent to that of the elephant, and bees are the ones which are the electrons. Now the question comes: why suddenly bees are coming to the elephant? The reason is that there is some sugar, or let's say some jaggery or some sweet sauce that has been poured on the trunk of this elephant. Okay, and as a result, these bees, they are getting attracted. Okay, so you can take this as some sort of like an electrostatic attraction force also. Okay, which is somehow binding them together. Now this elephant is moving and bees are also moving. But since elephant is much heavier compared to the bees, that means it will move much slowly compared to that of the bees. Okay. So this means that by the time the let's say, okay, so I'm just amputating the leg. Okay. Okay, so I'm putting little bit of final touch here. Okay, okay. So now this elephant is moving, and these are also moving. Now, since elephant moves much slower compared to that of the bees, so usually bees, they will have a much larger amount of time to respond to the motion of the elephant. Okay, so the time scale of the motion is different. So let's say in any condition, if the elephant makes a move, or let's say goes one step ahead, even if the bees are not aware of this, at any point they can quickly readjust their position such that the relative distribution of the bees and the elephant, it remains same. Okay, so is this part clear? So here
Yes,
what is
sir.
happening is that bees, they're adjusting their position almost instantaneously to any kind of movement of the elephant. So here now replace these bees by electrons and the elephant as the ion. Okay, so which means that the ionic motion will be much slower compared to that of the electronic motion, which means that at any given point of time the electrons can adjust their position compared to the motion of the ion, or in other sense we can say that from a, let's say, third frame of reference, or let's say another frame of reference which is not the ion or not the electron, if I'm sitting outside them, at any point I will not see any difference between the relative position of the ions and electrons. Okay, so is this part clear? Okay, no one is answering.
Yes, sir.
Okay, so now, so this is a very strong assumption actually, because as you see there are basically multiple motions involved here, so this will give us quite a good help. So now let's assume that initially electrons are in their ground state. So this is the most stable state, so they are not making any kind of transitions. But the ground state of the electrons is deformed by the ionic displacement. Okay, so although electrons are not moving, but if there is a motion by the let's say ions, or motion of the ions, then this will be perturbed. So let us first define few entities here. So let's say in the left hand side you can see there are several coordinates which are mentioned here. So let's say small ri, it denotes the position of an electron. Okay, me is the mass of an electron. Ri, capital Ri, this is the position of the ion, and capital M is the mass of ion. Okay, so now here you can see actually these electrons and ions, they are actually let's say distributed, and basically let's say there will be more large number of electrons and everything, so that's why we have a large number of R also here. Now if I want to write down the total Hamiltonian of such a system, then we will have two parts. So one is the electronic part and other is the ionic part. So this Hamiltonian will be a sum of Te, that is the kinetic energy of the electrons, plus Ti, that is the kinetic energy of the ions, plus Vii, which is the ionic interaction, plus Vee, that is the electronic interaction, plus Vie, which is the ion electron interaction. Okay. Now I can write down the operator expression of them. So Te, which is the kinetic energy of the electron, that I can write it as equal to minus sum over h bar square by 2 me del 2 del Ri square, and then Ti will be minus h bar square by 2 capital M del 2 del Ri2. So here this is capital R. And then the ionic interaction, so this will be a repulsive interaction, so that is why it has a positive sign. So which will be half square divided by 4 pi epsilon naught sum over L and L prime ZL times ZL prime and RL minus RL prime. Okay. So here ZLE is the ionic charge at the site L. Okay, so you need to keep in mind that here we are talking about more than, let's say, one ion here. Okay, and this half factor is included here to take into account the kind of doubling, or let's say the double correction. Similarly, we can write down the expression for electronic interaction. So this will again be some sort of a repulsive interaction. So this will take the form half of sum over ij 1 by 4 pi epsilon naught is square divided by ri minus rj. Okay. So now let us define some sort of a collective symbol. So let's say R here, it is being used to denote R1, R2 up to Rn. So all the electronic coordinates, and the capital R is actually being used to denote all the capital, let's say, ionic coordinates, that is R1, R2, R3, all these things. Okay. So is there any question up to this? Okay. So now we have got the Hamiltonian and the expression for different terms. So what we have to do is that we have to solve the time independent Schrodinger equation, because we are trying to find out the stationary state. So H psi will be equal to E psi okay. Now, as we are explaining for I think last two classes, such a system finding the exact psi is difficult. So we have to decompose psi. How we will do it? So we have to take the contribution from different components. So let's say the psi will be made to be a product of two different terms. One is I capital R. So this is the ionic wave function, and then we have psi E R sigma R. So this is electronic wave function, and here it contains the position part and the spin part also. Okay, but for the moment we will ignore the spin part. Now, as we said that we are defining these collective coordinates, so here we are assuming that for the moment ions are frozen at coordinate r. Okay, so if that is the case, then the kinetic energy term will be 0, which means that we will have here three terms, that is Te, there is the kinetic energy of the electrons, and then electron interaction potential, and then ion electron interaction potential. Psi E R, which is a function of small r and capital R, will be equal to E times psi E times which is a function of R. Okay, so this E is basically the energy of the electrons when ions are fixed at position R. Okay, is it clear? Okay. So now I'm going further. So H psi will be basically equal to these three terms, T plus T. Okay, so in general, this is the thing, that H psi is equal to T plus Ti plus VII plus VE plus VIE and chi I psi E. So this is the total wave function, of course. And here, basically, since we have got rid of the ionic part here, so here we have only three terms, that is Te and then Bee and then Vie, and yeah, basically we are just expanding it, and then we are again writing down this thing. So it's equal to E. Okay. So now here basically we have two terms. So basically we are splitting different terms. So the second term here is minus h cross square by 2m del RL plus del psi E del RL chi I R plus psi E del chi I del RL plus VII chi I psi E, and that actually will give us this particular form. So here actually you can see that basically we have So this term actually, so this will be the second derivative of psi e with respect to Ri because of this part. Okay, so I think I am kind of overlapping it. Okay, so here, okay, and then I have also another term which so it's like a square plus b square plus 2ab. So here this term will be counted twice because we will get one from here and another from here. So basically this is a product of these two, so we are taking the derivatives. Okay, then we have the second derivative of this equation. Okay, and then VII, Psi, and Chi. So please do this exercise at your home. So I'll share the PPT because it's kind of a little bit tedious to read this thing. Okay. So now what you're doing is that you are substituting this particular equation, equation number 10, into equation number 9, that is here. Okay. So if you do that, then you will can actually again simplify this thing. So here you will basically take this product of derivatives, that is del psi e del RL times del chi I del RL, this particular product term, and the second derivative of the electronic wave function with respect to RL square in the second basically in another bracket. Okay, so you have basically two different terms here, and with that, now what you are saying is that if the terms in this curly bracket, that means this terms which I have just mentioned here, that means this particular box term, if we ignore this, then this chi IR can be made to satisfy this particular equation. Okay, so remember this chi IR is basically the wave function of the ionic part. Okay, so here what we are saying is that the first term, okay, it has basically like the square bracket term, we have of course potential energy, kinetic energy, and then chi I. So if the second term can somehow be made vanish, then we get this particular equation which is only be satisfied by chi I r. Okay, so we'll later come up and see this thing again. So if that is the case, then we can write down H psi e chi I will be equal to E psi e chi I. So here EEL will be the total energy of the electrons at position R, and these energies can be easily computed within the framework of density functional theory. Okay, which we will again come back later that what is density functional theory at the end of this. And EER, it works as a glue to bind the ions. So because VII is repulsive. So now actually it can be shown that the terms within this bracket is negligible, and the ionic wave function, it describes the ionic motion, and psi e, it represents electronic contribution if ions are fixed at R. So electrons follow the ionic motion adiabatically in that sense. Okay, so this approach could be generalized to include the complete set of wave function, where we will get a product of basically electronic wave function and the ionic wave function, and we are summing it over a set of n, where n denotes the state index. Okay, so if n equal to 0, then this will be the ground state. Okay, so this is what is called as the Born-Oppenheimer approximation, and it works very well for semiconductors and insulators. So people have compared it with some experimental data that was available, and there they have seen this thing, that the result of the experimental data and the calculated or computed data, that gives a good agreement under this assumption. So the energy gap typically in such systems is of the order of electron volt. So nuclear motion cannot excite. So what it says, nuclear motion cannot excite electrons to higher energies. Okay. However, for metallic systems, the excitations can be created at vanishingly small energies. So here, Born-Oppenheimer approximation can break down. However, in first principle simulations of metallic systems, you can actually solve them. But here also you have to be careful if you are using Born-Oppenheimer approximation for such system. Okay, so I will not get into the next part now. So let us actually quickly go back and see what we have actually done. Okay, so let us first see basically what we have done. So we have, so idea is clear, we all know. We are just taking different routes. So the approximation here is that we have ions and we have electrons, and both have independent motions. Okay, what we are trying is that we are decoupling them separately. So electronic motion and ionic motion, we are treating them as different entities. So there is no interdependence. That is the thing. Okay. And now, since the electrons are much lighter compared to the ions, so we have assumed that the relative motion of the electrons with respect to the ion, it does not change. Okay, or let's say from a third frame of reference, it will not show any measurable change. And then here we have actually defined different coordinates, and let's say mass, of course. So r small ri is the one which denotes the electronic position or the coordinate of the electron, and me is the mass of the electron, and capital ri, it is the ionic position, and capital M is the mass of the ion. Okay, and here we have considered all possible interactions which are possible, which are kind of existing in the system. So there is kinetic energy, then that has again two parts, so kinetic energy of electrons and ions, and then we have ionic interaction and electron interaction, and then ion electron interaction. Okay, and then we have different forms for them. So the kinetic energy, of course, it will be minus h cross square by 2m del square, and then ionic interaction, or let's say the electrostatic potential, that will follow the Coulomb interaction rule. Now we have defined some collective symbol, that is small r and capital R, to define the coordinate of the electron and the ions. Okay. Now another thing what we have done is that we have decomposed psi in terms of, so this is a product of two different functions. One is the electronic wave function and another is the ionic wave function. And then we wrote down the Schrodinger equation. Okay, so here actually at the bottom you can see this is the complete wave function, or not wave function, basically Schrodinger equation. Okay, and on the top you have the same equation when let's say ions are frozen, that means there is no ionic motion. Okay, so equation 8 actually tells about only the motion of the electrons. However, at the bottom here we have the general equation. Okay, so here in the H side you can see there are all these terms, that is kinetic energy term of electrons and the ion, and then ion-ion interaction, which is electrostatic interaction, then electron-electron interaction, then we have ion-electron interaction. Okay, and this is the total Hamiltonian. Okay, so here actually again we can let's say decouple this particular expression into as into a sum of two different terms. So in the first part we have TE plus VEE plus VIE. So here you can see there is basically 1, 2, 3, 4, 5 terms here. Okay, within the bracket. So here in the first bracket we have basically 1, 2, 3 terms, that is TE plus EE plus IE. So this takes care of the entire electronic part. Okay, and in the second term we have basically the kinetic energy term of the ion, so that is minus h square by 2m plus del to del capital R I square, and the ionic interaction. Okay, so here you have two terms, so total 5 terms are basically decomposed into different brackets. And of course this is the total wave function which is present here and which is also present here, so that equal to E psi. Okay, so here you can see that is our equation number 9. Okay, so up to this, is it clear? Okay, now we are first looking at the second term, that is the term which actually denotes the motion of basically motion of the ions and the interaction of the ions, ion interaction. Okay, so if we look at that, then basically we can kind of like, so we are expanding this. Okay, so here we have psi times chi, and then we are just taking the derivative, so we have basically del to del RL, and then this partial derivative we can basically, we just take the derivative and then you end up with this expression. Okay, now you substitute this into the mother equation again, and then you again get this, and then you get this big equation. Okay, that is equation number 11. And now what we are saying is that if somehow we can make the second term to be 0, that means psi e del RL del chi I del RL plus del 2 psi e del 2 RL square chi I, that entire term has to be 0. If that we can do, then we will get this particular equation, which is our equation number, let's say 12. Okay, so this is a very simple kind of expression we will get, like kind of h psi equal to E psi, and from there actually you can find out the energy or wave function, all these things. Okay, now here the question comes, under what condition I can make this bracketed term to be 0? Anyone tell me whether it is justified to say this? So is the question clear? Okay. Am I audible, by the way?
Yes, sir.
Okay, so you see in this term we have basically, there are quantities. Okay, so del psi del RL times del chi I del RL. Okay, and then in the second term we have del 2 psi del RL square. Okay, so you see del psi E del RL. What is psi E? This is the electronic wave function, right? Or the valence electron, to be specific. Okay, and what is del RL? RL is basically the ionic coordinate. Now try to think of the elephant and bee picture. The elephant is trying to move, but the time scale is so large for that within the time scale the bees can at any point move. Okay, so here if del RL is changing, this psi E will not see any difference. Okay, because the relative motion is basically the relative scenario, or let's say the relative position of the ion and the valence electrons or electron is not changing. So we can simply say that there is almost negligible variation of psi E with respect to change in RL. Is it clear? Okay,
Yes, sir.
so we can assume that to be 0. So if that is 0, then this term will be 0 itself. Okay, see, we cannot make the second term 0 because chi I is the ionic wave function. Okay, so ionic wave function will of course have some variation with the change in ionic coordinate, right? But the first term can easily be made to 0, or it is giving very negligible contribution. So that is why the product will also be negligible. The second term will also take the similar kind of contribution, and it is rather the second derivative. So if psi e does not have any measurable variation with RL, of course the second derivative will be even lower, right? Which means that this term can again be ignored. Which means that both the terms within the bracket will give almost negligible contribution compared to the first term itself. Okay, so we can simply ignore it under this assumption. What is the assumption? The assumption is again that we have decoupled the ionic motion from the electronic motion. Okay. So in Viva, you might be asked this question: what is Born-Oppenheimer approximation, and what is the consequence of it? Okay. So this is the consequence. Basically, we can decouple, and that is why we can get rid of these product terms, okay, which are interdependent, kind of like psi e with capital R, these sorts of things. So then we got this nice equation, and from there we can actually calculate EE is the total energy of the electrons, and DFT can easily help you. So basically, yeah, that is the thing. And here, so we have actually gave little bit of explanation that psi I is giving us ionic motion, psi I is giving us electronic motion, things like that. And we can actually find out the total wave function if we make the product of both of these, and that we can put it by some level that will be the state index. Okay, and in reality, this approximation, it works quite well for semiconductors and insulators where there is a band gap, but for metallic systems, this does not necessarily give us a very good answer. Okay, so this is always true. We will see that every method has some limitation, and that of course is inevitable because we are working with an approximation scheme, and approximation scheme, or let's say any approximation, it is good for certain systems and it is not so much good for certain other systems. Okay, so any question at this point on this? Okay, so if not, then I'll say you please read these things. I'll share the PPT and you can also read some books. Okay, and that will kind of help you. So this particular section, I think I have taken from the book of Dr. Rajendra Prasad, and there is another book actually. So you can actually read it, and of course I'll share the PPT. Or if you have any other lecture material, you can also cover it. Okay. So I'll finish it at this point. Huh? And please let me know if you have any question. Okay. Okay, bye.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.